Welcome back, everyone. Our final speaker today is Vinueza, a practitioner in data science, quantitative risk analysis, and decision analytics. This talk is entitled Exploring Monte Carlo and Machine Learning. In this session, Guz will discuss how Monte Carlo simulation and machine learning can work together as complementary tools, combining probabilistic modeling with techniques such as CART and K-means to better understand patterns and risk data. Guz, thanks for joining us today, and thanks for all your help today. The stage is yours.
Thank you, Jameson. Let me see. Can you see my screen?
Looks good.
Yeah.
Excellent, good. And thanks everybody for staying. All the people that are saying thank you. That after all the issues that we had today, you're here. So thanks. I won't be long, and I hope this is helpful for you guys. I think that we have like 30 minutes, right, Jameson? So I will try to make it in like 25 or something, but this is something that really passions me. It's something that I really like, and there are two rationales here, and why is it that I wanted to talk about this is one is how to spot overlooked risk drivers, and I saw in Peter's presentation that he talked about drivers, and if you saw Francois' presentation, oh my, it was just about the drivers, right? How is it that we want to identify better the drivers and link them in somehow in the Monte Carlo simulation model and select the right drivers. We were talking about correlations. We were talking about all these things that today we wanted to give you a framework. You see that hopefully when I finish my presentation, you can connect the dots and say, well, now I have a few tools that I can use to improve my driver selection, my correlation coefficient selection, and things like that. So thanks both for your outstanding presentations. And the other is to have more defensible data-informed cost and schedule risk models. That's what I wanted to present for you today, right? To you today. So why is it that this matters? Because normally these are the variables that we have, right? It's like the typical iceberg, right? And you have the visible drivers, and sometimes you have hidden drivers. Most of the time, you will have experts doing the driver selection, right? It's like you have you want the drivers, you want to see which drivers are there, but you can sometimes miss subtle drivers, right? And complex relationships, right? Because one thing is to have a simple linear, maybe very long cost budget, but the other is to have, like Peter was showing, or like Francois was showing, very difficult and complex models, right? And sometimes you will miss because they are non-linear, right? You have disruptions, you have ranges, you have different formulas on top of them that don't make them real linear. So the results that you're going to get are as good as the drivers and dependencies you put in, right? And that's what happens, right? That with machine learning, and that's what I wanted to do. This is a new line of research for me. So these are by no means, like final results. These are initial results, right? That we can use machine learning to surface and to make them create, identify patterns in historical projects that perhaps humans overlook. On historical projects, and this is applied to a project portfolio, but this could be historical information, right? It could be anything, right? That humans, we do overlook this, right? So we have the visible and the hidden drivers, and sometimes hidden drivers relationships, right? Typical pain points, right? In real projects, sensitivity results, right? So you see, if it runs to the team, sometimes you generate some sensitivity results and they don't like it, or we don't like it. Overconfidence, that's sometimes they are neighbors, right? Narrow ranges, weak modeling, right? We just like the model to be finished. So we have this overconfidence. Well, this is the 10th time we do this. Why is it that we're going to get it wrong, even though we got it wrong the 9 times before, right? Risk registers sometimes, or the majority of times, they miss systemic drivers. Low credibility, you see that with executives who lack trust. So these are a typical pain point, right? Because you were wrong the last time, so why is it that you're going to be okay this one, right? And finally, black box inputs, right? So sometimes the outputs are unclear or opaque, and many times this pain point, it's because of lack of education, or sometimes we don't just know how to communicate. So there are the two ways, right? We have people that don't know how to communicate the result of a Monte Carlo simulation, and then we have sometimes the people, the stakeholders, they don't understand it. So all these pain points are present when you do modeling, right? So the proposed methodology, and this proposed methodology is going to go here, most likely to the sensitivity results, to the overconfidence, right? And sometimes it could be used here in the risk register. The methodology is straightforward, and I want to locate it here, right? You see that you have historical data. If you go back to Peter's presentation, remember that there was a question, how is it that you select a distribution, right? Sometimes you have historical data, and for this you use the Bose fit analyzer, right? You use it, it's perfect. You have historical data. But sometimes we just skip this machine learning analysis, and then we have the inputs, right? And then we go with the model, the Monte Carlo simulation, and the decision metrics. And we as experts, right, we tend to be a little bit overconfident here and say, well, these are the two variables that are going to be included. So you just generate maybe a correlation matrix there, or keep this with a factor that is going to multiply the two, etc. So you see, we keep Monte Carlo as the uncertainty engine, right? So please don't think that this methodology that I am proposing is going to replace Monte Carlo in any way. But we add a machine learning layer upstream, right? Before we even generate the inputs, because we want to know that the underlying relationships that we have in the variables, right? Use interpretable machine learning. So that means that I chose 3 algorithms of machine learning, which they have feature importance, clustering, and dependency analysis. And if you're familiar with machine learning, you will see those in the next slide, right? Predictions are not required at this moment, right? This is just focusing on the help of machine learning on how to set up and how to identify drivers relationships, right? And then, of course, we can translate the machine learning insights into drivers, ranges, and dependency structure. Now, the 3 algorithms that I chose was one, decision trees, or CART. You remember CART is classification and regression trees. And this one has feature importance, right? Random forests, thousands of cards, right, together, much more robust, right, than a decision tree. So we can have also the feature importance there. And then unsupervised, from the unsupervised learning process, right, we got the k-means to get classifications, right? Classifications or aggregation, right? Meaning I am going to look for patterns inside the data that most likely the experts are not able to see, right? So you see that we have these 3 data. Here, I forgot to mention that the decision tree also has this structure, and this structure may make it very easy to read, right? So it's very important that you see that I'm getting the best of these 3 algorithms from machine learning, and these are basic algorithms, right? We're not talking about neural networks or anything like that. This is, if you do data science 101, these are the 3 algorithms that you will learn, right? So that I didn't want to be that complicated, right? Now, again, so where is it that machine learning is going to fit into this risk workflow? First of all, the baseline model in Excel, like the one that Peter or Francois showed, they're going to be the same. They will remain the same. They are not going to go anywhere, right? Before the simulation, this is how where the changes come. Before the simulation, we are going to use machine learning to validate the drivers and detect missing drivers, right? So we're not going to use machine learning for predictions. We're just going to use feature importance and clusters to identify relationships, right? So we're going to take a different, you see that things are as you see them. And in this case, we're going to see with the eyes of a machine learning algorithm, but we're going to look for other relationships. We're not going to look for the prediction, right? So in this case, the contribution of each one of them, it's here, you see, complement variance-based sensitivity, increases confidence that observed drivers are structural rather than model-specific artifacts, and finally, aggregation, which is what I said before, right? So now that we have these 3 elements, right, I'm going to show you how each one of them. So a quick, and I am sure that you know this more than anyone, right? A quick reminder of how Monte Carlo simulation works. Remember that you had a model. This model has some variables. The variables we need to identify the interrelationships between these variables, and these variables, they have distributions. The model then, it's run thousands of times. The orange box that you have there, right? It's run thousands of times, and this is what we were trying to do, right? Thousands of iterations or times, and this is where you have model risk as the machine behind them, right? And then the result is going to be a table, right? It's going to be a table like this, right, with all the results. And on top of this table, you would generate a histogram, or you would generate a tornado chart with all the artifacts that model risk can provide, right? And that is the main idea, right? So what Monte Carlo does well, you see, it turns uncertainty into probabilities. So you can say, well, what's the probability of, in this case, for example, what's the probability of my NPV being negative? 10%. That means that I have 90% probability of being positive. That means that my project is really, really, let's say, well put, because it's not as risky. And for example, here for my IRR, I can do the same, right? What's going to be my IRR at certain level of confidence? It supports the contingency, and that's exactly what we saw in the previous presentations, and confidence level reporting, right? You have my P80 is going to be this, or my P50 is that. Remember exactly what Peter was showing. It shows trade-offs. You can do scenarios with the sim tables, right? And enables sensitivity analysis to focus on mitigation efforts. So after you run the simulation, it's going to be very common that you see some tornado charts, and these tornado charts, after you run the simulation, these tornado charts are going to give you, right? They're going to give you focus, right? That's what they are going to give you. Focus. There, where is it that I should put my attention? Where should I locate my resources, etc.? But Monte Carlo simulation struggles, and this is one of the, I wouldn't say weakness, but this is something that this is an opportunity here, that because Monte Carlo does not discover missing drivers, right? Monte Carlo runs the simulation with the drivers that you have. If you don't add correlations, for example, and this is what happens with, I don't know, 85% of the people that run Monte Carlo, they don't ever use correlations. Why? Because Monte Carlo doesn't require it. It does not discover these missing drivers. If you don't add them, the drivers are not going, the variables that you have them there in the model are not going to behave like that, right? It depends on the analyst defined structure. You see, often uses simplified dependencies, and it can hide model fragility behind very impressive looking charts, right? Because everything looks so nice. You remember, on top of Excel, which generates everything nice, you have model risk, which has an outstanding graphical capability. So if you don't model these drivers, perhaps you're missing something, as one of you asked in the chat before, right? So there's a driver gaps problem, and projects sometimes fail because of the combination of small drivers, not one big event, right? Drivers can be indirect interfaces, learning curves, volume changes, procurement latency, right? And hidden dependency are often creating fat tails, right? Rare but severe outcomes, and we need tools to detect these patterns systematically. So the proposal is to add this type of addition on top of the methodology that you use right now to generate Monte Carlo simulation models. Why is that? Because this is going to enrich the model that you have, right? So why is it that machine learning helps? Because first of all, and this is like a funnel here, it learns from historical data. That's one thing. Of course, and then you will say, but I only have 2 experts and we don't have historical data, so maybe this methodology is not for you yet, right? Because you don't have enough information, right? That's one thing. Of course, you can get what we call feature importance, right? And this is something that you use in CART or decision trees, right? Or random forest, which are no more than thousands of decision trees, right? Where basically it says, well, these are the variables that influence the most to the output, right? You have a risk archetypes or risk groupings that you can find when you use k-means, right? and you will be hopefully able to detect nonlinear relationships, right? So these are the three. This is like the dream, right? I have historical data. I can run feature importance, and this is going to give me sound and robust results. I can get risk archetypes and nonlinear relationships as well, right? Some important guardrails before we start is that, first of all, association is not causation, so we have to interpret it carefully, and this is part of the research, right? Not because I have, let's say, 3 variables that my expert identified, and then I have 2 more, so that means that the 2 more that I found are the cause of the ones that we already identified, or vice versa, right? We just have to be very careful. The thing that we're doing is looking for interesting relationships, right? So that's one thing. Second thing is data quality. And data quality sets the ceiling, right? Garbage in, garbage out. As Peter was saying, the decision quality, right, is going to be based in the data that you have. If the data that you have is bad, so how is it that you can expect something that's going to be good? Hopefully, we can keep the models interpretable for governance, and the expert judgment is always essential, right? Machine learning is not going to be a replacement, but a complement of that. So step by step, how is it that it works, right? For example, what predicts cost overrun? What predicts schedule slip, right? So we'll have to choose the outcome metric, right? In this case, the schedule overrun, for example, or the delay that we're going to see in the examples. Decide what's the unit of the analysis, the project, the package, the portfolio, the activity, the business unit, and define success criteria, like, for example, improve sensitivity accuracy versus the objective outcomes. Step number 2 is prepare a clean data set. As we were talking before, data quality is crucial. So we have to standardize definitions, we have to handle missing values, separate inputs available, etc. You see, these are things that normally you don't do in a Monte Carlo simulation model, right? Because you just have the model and run it. You just have the distributions. But now, as you're going to have machine learning on the mix, right? You just need this, right? You need in this case, the unit of analysis, the success criteria for the decision of the drivers, then the clean data set, revised, right? In the machine learning, if you have in the supervised machine learning, you have something that's called feature importance, right? So you will have to have at least certain number of data points, right? So you have some good interpretable model, like a tree base, right? Like the one that we have in the red. We just have to be able to identify like these surprising drivers. This is very important, right? Because sometimes we are so used to do things that we don't let ourselves surprise, right? But let's say that you're going to do a model that it's very complicated, and maybe a new variable arises as very important, and you've never thought about it. So we have to go back to I wouldn't say innocence, but we should let ourselves surprise. Sometimes we just don't see relationships. And of course, we have to use the results to update the driver list and the model structure, right? That means that if we find a different driver in the model, that doesn't mean that I don't know, like this is the typical question I always get. So we're going to include it into the equation. We're going to add it as a filter, add it as a correlation matrix, etc. We need to dig deeper and identify case by case what to do with these drivers. Finally, if you have a supervised model, and if you're lucky to have this feature important, that's great. Otherwise, we can use unsupervised models and do the archetypes. Remember the risk archetypes. So we are going to let information decide how to aggregate automatically. And that's what you do with this algorithm. This is called the k-means algorithm. And it's not like you're going to generate the code and the logic of that. This is all built in Python. If you like to do it, maybe you're wondering how is it that you did it. I did in Python because I'm a systems engineer, but you can just put the data in. If you use, I don't know, ChatGPT 5.4, if you use Claude, sometimes in the paid version they work better, and they can do this for you. So it's not like you have to learn how to program. Of course, if you can, of course, I would recommend to do it. But other than that, you can do it yourself, very, very simply with the new tools that we have to reach our hand, right? So in this case, for example, if we do an unsupervised machine learning model, we're going to use the clusters, this self-grouping list of variables, right, or list of data that we have. Right? You use what we call clusters to tailor distribution and correlations by archetypes, right? And for example, here, let's say that we're doing projects as the example that we have, right? So as we have the projects, they could be, for example, yeah, you go. We can say, well, which past projects are most similar, and maybe they are going to be grouped. Imagine this is the cluster 1 of projects, this is cluster 2, and this is cluster 3, right? And here we have some projects, and in each cluster we have a subset of projects. So maybe, and we don't know why, because this is going to be automatically, we don't have control on that. These projects are going to be related and closer together by using a different variable that we didn't think about. And this is something that only machine learning can bring. Right? So that's why I chose these algorithms to be used. Then dependency discovery, for example, look for dependency among drivers, like for example, correlation, mutual information, model interactions, right? Sometimes spot share causes that tie multiple elements together. If you are familiar with, I don't know, ACE, oh, here you go. RP, I think it's 57R, right? It talks about the share causes, right? About the risk factors. If you have share causes, that's something that might be a potential contribution to it. We can convert it into a dependency structure, focus on dependencies, etc. Compare always with the expert's opinion, right? So the idea here, again, is not replacing the expert, but giving him or her an additional tool. That's the main idea of this approach, right? Now, how is it that it's going to work? We're going to get the raw Monte Carlo simulation insights here, right? They are going to come here, and most likely like a feature importance, like in this case, like a decision tree or like a group of clusters, right? Then we have to do the driver selection and say, well, we have these two new variables additional to the expert variables, right? What is that we're going to do, right? We're going to recalibrate the uncertainty, and going back to what Peter and Francois mentioned, right? Change the distribution selection, add some dependency there. Maybe we have to add a factor that is going to link all of these variables together with some equation. Sometimes we can have correlations added to the mix as well. That could be another one, right? And finally, we're going to check the simulated distributions versus the historical ones, right? So what happened if, for example, I didn't run these machine learning algorithms and I just go with the flow and I just do it as I always do, right? So these are the typical additions that you will do to your distribution process, to the distribution selection process, right? Common factor drive, for example, we have a practical, it's called the practical modeling pattern, and we have these common factor drivers, right? Where we have, for example, here, market pressure, which affects pricing and delivery timelines. Labor availability influences construction and engineering cost, learning curve here, change value, all of them influence. If you have all of them into the model, you will have a different influence level for each one of them, right? So each factor is going to influence multiple cost elements. If, for example, your experts say, well, for this model, only the market pressure is going to be available, then you run machine learning, and then you find out that the learning curve and the change volume were important as well, right? So how is it that you're going to do? And then you go back, right? You're going to do an additional, deep dive on how these distributions were set up. Maybe you were just saying, well, as I don't have information, let's take just the typical, right? Normal distribution, I don't know, 0.5% to multiply to the mean and some number there. So maybe you just were not caring that much when you have the drivers that are going to be very important. And that's the key that I wanted to overcome. That's the shortcoming that I wanted to at least improve, right, with this methodology. So first of all, case study, cost overrun in projects. We had like 50 fictitious projects, right? Historical data set where you have a traditional model versus a Monte Carlo simulation model. And the main idea is to see if the sensitivity rankings and outcomes align better with reality, right? So these are the 6 variables that we have, right? We have of course, a project ID that we have here, the direct cost, which is here, financial resources. There was a productivity factor or labor productivity index. We had the duration of the project, which is here. We had a steel price factor, a weather factor, right? And engineering maturity factor. So it depends on the project. You have all of this. And if you like, of course, I can share with you the models are very simple, and here we have the distributions that I use, right? For example, the I don't know, the steel impact steel cost was a factor that you will multiply by the steel price index, which you have here, right? And here you have the logic of the model as well. There's one equation that you have, and this equation that it's going to give you is going to give you the total cost overrun for the model, right? And here you have an extract of this, right? So you have, like, for example, a project that has 180 million, 2 years. This is the productivity index, steel price, engineering maturity, weather exposure, and this is going to be 14% cost overrun, right? And then you have all of these projects together, right? So the main idea was before, and this is the trick, right? Before you run your first Monte Carlo simulation model, right, to see if you can identify additional drivers. What I did in reality, because this is how I was able to find out all of this. Of course, I run the simulation first, right? This is my cost, right? My cost curve. This is my CDF, and it says that, for example, my PAT for the cost overrun is 58%. This was my 58% for my PAT. We had a mean like of 30%, right? All the variables are independent. I didn't include any drivers. And here what I did, I used the proportional contribution to spread tornado chart, which is outstanding. It's very simple to use. Why? Because everything is set up in percentages and they sum up 100%. So that makes it very simple and to use it to explain things, right? So here, the labor productivity and the engineering, they account for 87% of the risk. So this is after the simulation. You will remember, right? This is after the simulation. We have some results that could be considered our drivers, right? The labor productivity and the engineering, right? Now, what happens here? What I did, I took all this information that I showed you before, and I generated 2 models. One was this CART model, the decision tree structure, right? And for the decision tree structure, you see that the main variable here, the one that divides the risk, the CART, right, or the decision tree, is the steel price index. That is the root of the tree, right? So normally the root of the tree, right, is the variable that if you use it to classify the rest of the variables, it's the one that generates more gain, more information gain is called, right? So steel price index, you see that steel price index was here, right? Number 3. And you see here, the risk driver importance, it says engineering maturity, which was here. Number 2, engineering and steel price index. So the proposed approach will require analysis to run a few analyses before. The CART model to understand the important, steel price is the biggest one, and the random forest, which is more robust in terms of how it is from a machine learning point of view, right? Engineering maturity and steel prices as the main values, right? So machine learning recommends steel price and engineering. Monte Carlo simulation showed productivity as the main drivers with engineering, but productivity was very high. You see, it's 70% almost, right? So what I did, and I said, well, let's do what it could be a very first approach, right? And this is where the research has stopped, right? Which is, how is it that we're going to have a pecking order on how we're going to interrelate these variables? Because right now we have these variables, but as I think that Peter said, right? Sometimes when in the distribution selection, sometimes you don't have like a checklist, like a punch list when you say, well, you have this, and then if you have this, you go route number 1 or route number 2. If you have this or that, you go route number 3 or route number 4. Sometimes you just have to review the model. Or maybe research is going to show that there is indeed a route that we could use, but we don't have it yet, right? So what I did, I generated a correlation matrix between these three, right? Steel price, engineering, and productivity, right? I generated it, and I generated the model with a sim table, which is what Peter was showing. Say, well, without the correlations, right, independent variables, without the drivers, you see your P80 was 57%, and your P90 was 68. If you run it with the correlations, right, considering the relationships between the in this case, the variables, right? You see that P80 is going to be 62%, P90 73%, right? You have like a 7% difference in each one of them, right? So the good thing about this is that if we incorporate at the beginning, right, this feature importance or this decision tree elements that we had here, right, we're not going to get into a situation, because maybe you will say, yeah, but we can correlate all the variables, and maybe you will get the same results, of course, but then you will have to correlate all of the variables that I had here. Remember, all of them, and it's like 6 or 7 variables. Here I only had 3. Why is that? Because we already have the labor productivity, and the machine learning confirmed that steel price and engineering were important as well. Maybe I didn't see that here because it was very big. So that's why this confirmed my initial hunch, right, that I needed to do correlation on these 3 variables. And that's one of I would say advantages of the methodology, right? So one of these, right, is why is it that we're going to compare, right? Because we're going to align stakeholders on what truly drives model uncertainty. And that's what we wanted to do. Second thing, you see, is that if we have an importance comparison, right? And you see here, machine learning highlights structural drivers. But here, Monte Carlo simulation tornado charts, they're parametric drivers. Remember that this is after the simulation, right? After the simulation model, and this is before the simulation. So these are 2 different moments, right? These are totally different perspectives. So please, I will share with you the presentation, and because of time, I don't want to go deep into each one of them, right? And then finally, in this case, of course, we'll have to analyze it case by case. We have convergent risk drivers. So both analyses identify the same core drivers like engineering, right? But the one it was not a core driver was the productivity, and then we had steel price, right? So this is one case. And the second case that I have here, right, is the schedule delay. Remember that we talked about cost delay. Now we're going to have schedule delay. This model has these 7 variables, right? The contract type and location type that could be 0 or 1. And this is very interesting because you will have projects like this, right? When you have a different project portfolios, you will have contract types that are different, location types, and then you have sourcing, complexity about regulatory setup, the plan duration months, and the final schedule delay. And again, you will have this data here, plus you will have the information here on how is it that it was set up. For example, the simulated duration, you had 1, the regulatory adjustment, we have another distribution. And here, remember that we have project types and location types with some indexes here, right? So this is what we try to do now. We try to validate the final schedule delay months. This case is special, and that's why this pattern is because we had different combinations of contract type and location type, as I'm showing you here, right? So you will have contract type 0 and location type 0, or contract type 0 and location type 1, and you see you have 1 and 0 and 0 and 1. So you have 4 combinations, the ones that you have here. There are 4 combinations of projects in the classification, right? And you see here, so what I did, I generated an average for each one of them just to see them before we run the model. You see, so take a look here. The average of the regulatory complexity for this combination is 2. The plan duration months average is this, the multipliers, and finally the delay in the month. You see that 0 and 0 have the least delay in months versus 4.1, which is the highest in the 1 and 1, right? So you have 4 type of different patterns. Why is it that I did profile this? Because what I wanted to do is, let me go here and then I'll go back, right? What I wanted to do is to generate an analysis of clusters, right? Remember, a clusters analysis. And this clusters analysis, it should match, right? It should match the structure of the model. Remember, we're talking structure here because this is before the simulation. So this structure of the model that has 4 groups of projects that we're going to call clusters was indeed recognized very well. What I did before, and this maybe is part of the methodology, right? I run the model here. So this was the P80 and P95 for each one of them, right? In terms of the delay. Right? I took a look to the drivers as well. Take a look here. It's the duration and the regulatory multiplier, the most important variables in both, right? Duration and regulatory adjustment. Right? So I did this for the 4 models, and the same variables appear as the main ones here: the duration and the regulatory adjustment, right? Duration and regulatory adjustment. Right? So what I did, I run this model 4 times, right? Or with this, I call it what we call the sim table, as Peter showed. And we have this tornado plot showing the main variables. And then what I did, I run the model using machine learning. In machine learning, this is very technical. I just wanted to show you that when I run the model, the number of the 4 different groups of projects were identified, what we call the number of clusters, right? With something that's called the elbow, the silhouette score, both showed 4 as the optimal, which is great because that means that this project could be analyzed. And then what I did, and I'm not going to go deep into that, I generated some graphics for you see here, you have clusters, you have 4 clusters for each one of them, and then I could validate, for example, the complexity of each one of them, the duration in months of each one of them, what we have here. So for cluster 0, this is going to be the average of the complexity and the duration. But for cluster 1, take a look. For cluster 1, the complexity is much higher and the duration is much higher, right? In this case, cluster 3 also has a combination of them, right? So these are, remember, the groups or the clusters that I had before. In this case, what I did, I also generated what I call the dominant variable. And the dominant variable, it's a calculation, it's a graphical calculation that goes from each one of the centers of these groups. Remember that we had like little, you see, groups of variables, and inside them, we have something that it's called the centroid or the center, right? So what we did, we just measure each one of them, right? And the distance from each variable as to the center. And you see that we got, you see, the duration in months as the most dominant driver and the regularity complexity as well for the 4 groups. This matches the one that we got before, right? The one that we got before, which is good, right? Because what it says is that the variables that you were getting after that without doing anything are the same ones that you have in your structure modeling before you run the simulation. And that's what we wanted to show. Right. In this case, and because of time, because I shortened the presentation a little bit, I didn't do anything else because what I'm looking at is that the same variables that I have here are the same variables that I use there. So I don't need to do anything else. What happened if, for example, here I have a variable, a surprising variable, like for example, here, I don't know, weather or I don't know, provider or anything like that, that we didn't have before, of course, I will have to include it. How to include it, that's part of the future research, right? And of course, what I did is I took a look to the dominant drivers per cluster. These are the dominant drivers in total, and the dominant drivers per cluster are the same, you see, and they are in bold for each one of them, right? So what we did, and this is what I'm trying to show, is that we did a structural insight before the simulation, right? The clustering revealed project archetypes, right? Distinct project archetypes. Imagine that we didn't do that after that. Remember that that means that I will have these 4 project archetypes that I can call, I don't know, big projects, small projects, remote projects, close projects, etc. Right? And I got before I run the simulation, remember that this is how we have to run it. Before I run the simulation, I had the planned duration and the regulation complexity as the main variables. Then after running the simulation, I confirm, right, that the clustering identified the true structural regimes. Why is that? Because the variables were the same, right? That means that gives me more security, right, for the interpretation of the sensitivity results, right? And this is what I'm saying that. Right. Finally, what are the implications for model design? Right, that risk models should condition Monte Carlo assumption on cluster membership, right, rather than aggregate all projects into a single model. That's what I discovered here. The results were much better when I did that, doing it model by model instead of doing it at the portfolio level. So you remember one of the decision keys at the beginning of the presentation was, should I do it at the portfolio level or at the project level? Right? That reduces distortion, right, from averaging heterogeneous project types. Sometimes you see that because the models are so, the model information is so vast, we say we're going to average everything, and we cannot do that, right? We should not do that. We can do that, right? And of course, enables context-aware sensitivity analysis. Now, to finish, so let me finish here, and this is the main takeaways, right? First, the main project insights that we have from Monte Carlo simulation, from machine learning plus Monte Carlo simulation, right? We went from limited project understanding, which is here our starting point, where we have sometimes unclear project drivers, right? Or sometimes we just have to trust our experts, but sometimes the experts, as Peter super well explained, are very biased because they do that forever, right? So they get overconfident, they have proximity bias, they have all of that, right? So we apply machine learning to the project data, and hopefully or not, right, new prominent drivers will arise, and we have to incorporate these drivers, right, reevaluate this driver importance, and we have an enhanced project understanding, even if, like in case number 2, the drivers were exactly the same, or in case number 1, the drivers were a little bit different, right? Why? Because we have now more realistic outcomes, and this is what I wanted to show today, right? That with this simple methodology, you can generate an enhanced understanding of your projects. So with that, I will be open to questions, and thanks for your patience to all of you that are still here. If you have any questions.
Thanks, Goose. That was excellent. Ooh, we got some questions coming in.
Oh, good. See, I have my chat here.
Me too. Let's see if I can see this.
Thank you. It says, how do you choose the right number of simulation runs? Well, normally, and this is going to be open for the, I'm not sure if Peter and Francois are still here, but number of simulation runs, normally I do, these are my rules of thumb, right? Between 500 and 1,000 when I'm designing the model. Then 5,000 to 10,000 when I'm doing QA or socializing the model, right? Sending it to colleagues to try it. And then I'm trying to get the fat tails to be well profiled, right? If you know that you're going to have very, very low risk probabilities. So I will try these tails to be really well profiled. And then I will run maybe 10,000 to 20,000 when it's the project that I'm going to be making the decisions with. Right? That's what I would do. The analyst experience, as it says there, and some convergence level. I know that in model risk, you have also the convergence level calculation, and you have that into the help. You can use that as well. So I would say convergence and when you see that, for example, with 10,000 iterations, your P80 was, I don't know, 230 million, and then with 20,000, it was 230 million point 2. So you just reach convergence, right? You just have to stop there, because if you do 50,000 iterations, that's not going to change the results on a big time, right?